So source-free RL circuits means that in the circuit, you don't have any source. An inductor is acting as an energy source, supplying current and power and energy to rest of the circuit. This is similar to what we discussed, source-free RC circuits. In source-free RC circuits, of course, first you charge the capacitor, and then you remove the source, and capacitor starts acting as a power supply. So similarly over here, you basically charge an inductor. Inductor stores energy in its magnetic field, and then once you remove the source, inductor starts acting as an energy source, and it starts supplying current to the rest of the circuit. So what we are going to look at, we are going to first derive the equation of the current, the inductor current, that is going to represent how the current is going to change once inductor is going to start supplying power to rest of the circuit once you remove the source. And the equation is pretty much similar to the equation of the capacitor voltage when it is supplying power in a source-free circuit. So you will see that the equations are very same. The only difference you will see, of course, is the time constant. The time constant of RL circuit, the formula, is going to be different than what we have for the time constant in RC circuits, which was R times C. So that time constant formula is different. However, remember what we discussed about the time constant, the concept of time constant is still the same. That is, in an RL circuit, time constant of the RL circuit is going to represent the time during which the response of the inductor current is going to drop to 36% of its peak value. That time is going to be called the time constant of RL circuit. So we are going to look at the time constant, and of course we are going to solve some problems. So we are going to start with derivation of the current, inductor current, in a source-free RL circuit. So let's assume that we have, and I'm going to take the simplest case right now. Let's assume we have one resistor and one inductor. And I have a unit step function. Let's say I have a source Vs, and this source, we can assume any value. Let's say the source is Vu negative T, or V naught U negative, whatever you want to call it, V naught U negative T, volt. So this shows that at time t is equal to 0, the source is going to turn off. And before time t is equal to 0, the value of the source is V naught. V naught to 0 at time t is equal to 0. We have a resistor and we have an inductor. And since they are connected in series, in a source-free circuit, in the source-free circuit, it does not really matter. They will be just connected across each other. So if I remove, when the source goes down to 0, and I will short out this source, Vs, then series parallel doesn't really matter in that case, because it's just going to be two components connected, and the same current is going to be flowing through those two components. And we call this current basically ILT, that is the inductor current, but the same current is going to be flowing through the resistor in this circuit. So what we are going to do first, as we did in the case of capacitor, the first thing that we do is we find the value of inductor current just before the change is happening, because that value of inductor current is going to be the same as just after the change has happened. So at t is equal to 0 negative, the current value in inductor, if the current value in inductor will be equal to t is equal to 0 positive. Now, if the circuit is running for a very long time, like this circuit, it is running for a very long time before at time t is equal to 0, the voltage value goes down to 0. Then the inductor is going to be fully charged, and it will be acting as a short circuit. So it will have energy in the magnetic field, but the magnetic field is not going to be changing. And if the magnetic field is not going to be changing, that means the induced voltage or the voltage across the inductor is not going to change. And the voltage is going to be zero means that your inductor is going to be acting as a short circuit. And the current that will be flowing through the inductor, basically it's flowing through that short circuit. That current is important. That current will be constant. And that's why the voltage is going to go down to zero as well, because remember, voltage across the inductor, if I assume that this is VR and this is VL, then voltage across the inductor, remember, is equal to LdI over dt. So the voltage goes down to zero means that there is no change in the value of the current. So IL is going to become constant, and when it will become constant, the voltage is going to drop down to zero across the inductor, and inductor or the circuit is going to be at the steady state. So let's write down. So let's figure out first what will be the initial value of the current passing through inductor. So and that's the process that you have to do for when you're solving any problem that requires you to figure out voltages and current in an RL circuit after the change. Similar, the process is similar as we did for the capacitive circuit, RC circuits. So C, this is less or equal to 0 or 0 negative, but T is equal to 0 negative. This circuit is running for a very long time, which means inductor is acting as a short circuit, which means the current that is passing through the inductor will simply be, using Ohm's law, Vs over R. So the initial value, I naught, which is IL at 0 negative, will simply be Vs over R. Or Vs value is V naught, so V naught over R. And we'll call this initial current I naught. Now, when the source voltage goes down to zero, and it's a voltage source, that means now the source can be replaced by a short circuit. So T greater than 0. The source is going to be short circuit when you have resistor and you have inductor. So now they're connected in series, they're connected in parallel, it's the same thing, because they're just two components connected in the circuit. So R, L, VR, and VL. So if we apply KVL, VR plus VL is equal to 0. And we can write this down in terms of Ohm's law. VR is going to be IL times R, and VL, L DIL over dt. And this will be equal to 0. Remember, we are trying to figure out what is the value of IL for t greater than 0. So like we did with the derivation of RC circuits, we're going to do the same over here. We are going to write this down as we're going to take it on the other side of the equation, and we're going to write down ILR is equal to negative L di over dt. And then we can rearrange this as R over L negative times dt is equal to DIL over IL. So DIL over IL, if we integrate this and integrate the other side as well, negative R over L dt. At t is equal to 0, we assume our initial value of the current, inductor current, is I naught, and at t is equal to time t, our inductor current is ILt. So we solve this integral. Integral of dx over x is the natural log of x. The natural log of IL, ILt I naught, and this will simply be negative R over L times t. Natural log of ILt minus natural log of I naught, and natural log of A minus natural log of B is natural log of A over B. Natural log of ILt over I naught is equal to negative R over LT. We go ahead and take the exponent on both sides to get rid of natural log. So we're gonna get ILT over I naught is equal to e to the power negative R over LT. And this will give us ILT is equal to I naught e to the power negative R over LT, which we can write down in terms of time constant I naught e to the power negative t over tau, where tau is going to be L over. So when you put tau is equal to L over R, you're gonna get I naught e to the power negative R over LT. So this is the time constant of RL circuits. And remember, the time constant definition, as we discussed, is the same. It is going to be the time during which the inductor current is going to drop down to 36.6% of the initial value, which is I naught. That's going to be the definition of time constant. So this is the equation that we're looking for. The source-free RL circuit, the current is going to go down exponentially in each time constant. And generally, 4 to 5 time constant, it is going to be as close to 0 as possible. That's what we assume practically, as we discussed in the case of RC circuits. Of course, mathematically, is never going to go down to 0. It's going to go down to 0 at infinity. But practically, we take 4 to 5 cycle, and that's good enough time for us to assume that the current that the circuit is at now steady state, and the current has gone down to 0. It's going from I naught, and this is approximately, that's gonna be approximately tau 36 0.36 I naught, and it's gonna take approximately, let's say, 4 or 5 time constant before it goes down to almost 0 ampere. So this is the relationship of the inductor current and the time constant and the initial value of the inductor current. Now, any problems that we are solving for the natural circuit or source-free circuits, of course, we have to make that circuit without any source. That is L, and then no matter how many resistors are there, we take the equivalent of those resistors and put only one resistor with L, like we did again in the case of RC circuits. And then we can easily solve the circuit. Again, remember that if the circuit is running for a very long time, and if the inductor is there, inductor is going to be acting as a short circuit, voltage across it will be 0. So you can replace the inductor pretty much by a short circuit. Assume that the IL current is going through it. IL current is going to be a constant value in that case. And circuit laws can be applied, of course, to find the value of that current and voltages or whatever is in the circuit. Let's go ahead and work on our first problem. Problem 1. Okay. Let's say we have R1, R2, L, R3. Switch is opening at T is equal to 0. And then we have a voltage source. Vs equals 20 volt. Let's assume R is 3 Henry. L is 3 Henry, sorry. R1 is 20 ohm. R2 is 44 ohm. And R3 is 33 ohms. Inductor current is going through the inductor. So what we need to do is, in this case, determine first. Let's say determine the inductor current for t greater or equal to 0. So expression for inductor current for t greater or equal to 0. Second thing, inductor voltage expression for t greater or equal to 0. Third, power dissipated in R2 at let's say we'll decide time because time depends on the time constant. So I don't want to take a very large time such that the current has gone down to 0. So power is going to be pretty much 0 at that time. So we'll decide when we look at the time constant. When we calculate the time constant of the circuit, then we'll decide at what time we want to calculate the power in R2. Of course, method is going to be the same to calculate the power. Just we can plug in that value of time, so we know what exactly is the power dissipation at that exact instant of time. So we'll come back to that specific time value that we want to calculate the power in R2 at that time. Okay, so again, when you're solving the circuit and you're trying to figure out what is the current value passing through the inductor at for t greater or equal to 0, the first thing that you do is you find the initial value of current in the inductor. So you solve it for t less than 0, or you find the inductor current at t is equal to 0 negative. Now, assuming that the switch is closed for a very long time before it is opened at t is equal to 0, inductor is fully charged. That means inductor is acting as a short circuit. When inductor is acting as a short circuit, and it will be in parallel with R2 and R1, that means R2 plus R1, both resistors, they're going to be gone. There is no current flowing through R2 and R1. And all the current that is supplied by 20 volt source is going through R3 and inductor. So it's very easy to find the initial value of the current using Ohm's law. It's simply Vs over R3. I naught will be Vs over R3. Let's go ahead and put values in MATLAB so we can Okay, so my R1 is 20, my R2 is 44, my R3 is 33, my inductor is 3, and my Vs is 20. So I naught is Vs over R3, 0.6061 or 606.1 milliampere. 0.6061. And this current is not going to change at t is equal to 0 positive. That is after the switch is going to be opened. So t greater or equal to 0. IL0 negative will be equal to IL0 positive is equal to I naught. And now when the switch becomes opened, the energy stored in the inductor is going to start dissipating through R1 and R2, because when the switch is opened, of course, R3 is gone because it is connected in the open branch. So your circuit is reduced to R1, R2, and L. So it is very easy to find the time constant and solve the circuit. This is your circuit. R1, R2, and L. Now remember, the voltage initially, when you are charging the inductor, of course, voltage was 0 across the inductor. But initially, when there was voltage, the voltage was such that it's going to be positive voltage on top and negative voltage at the bottom. And the equation that we wrote basically for ILT is the positive voltage on top and negative voltage at the bottom. Voltage across inductor can change instantaneously. Current cannot. So when inductor starts acting as a source, current direction is still going to be the same. Current is going to be coming from the top and going through the bottom because current cannot change instantaneously. However, the voltage is going to flip. Now it will start acting as a source. So this will be the direction of the voltage that is across the inductor when it will start supplying the current. Current direction is not going to change. Of course, current will still be flowing through that in the same direction, through the inductor in the same direction. Resistance, of course, the current direction is going to be opposite because now inductor is your source. So what we have to figure out is, first of all, your inductor current, part 1, inductor current, and that is I naught e to the power negative t over tau. Okay, tau is, in this case, R1 plus R2 L over L divided by R1 plus R2. Because R1 and R2, they are in series. So tau is L divided by R1 plus R2. 0.046875, so 46.875 or 46.9 milliseconds. 46.875 milliseconds. So now we can say that we want to calculate the power. 1 tau is 46 milliseconds, so let's say at 10 milliseconds, so within 1 tau. What is the power at 10 milliseconds dissipated in R2? So the equation of ILT is straightforward. 0. Equals 0.606 e to the power negative t over tau ampere. Of course, tau is here, so you can put down tau here, but as long as you calculate it, that's fine. Number 2, part 2 is we have to calculate the voltage inductor for t greater or equal to 0. VLT. Now, the voltage, inductor voltage, if I go back, actually, no, that was the last lecture. When we establish the relationship of the voltage and current, PL, then the voltage is L di over d. That is, the current is entering on the side where the voltage is positive. If the current is leaving the side where the voltage is positive, then you will have to write down negative L di over dt. Similar thing that we discussed in capacitor, that if current is leaving the side where the voltage is positive, which happens when the capacitor is supplying, of course. Why I'm showing an inductor as a capacitor? Let's go and change it. Oops. Interesting. Should capacitor and keep calling it inductor. Here it is inductor. Okay, good. All right. So as the same thing as capacitor, voltage cannot change instantaneously. So the capacitor voltage, if you're charging a capacitor, voltage positive is on top. If you remove the source, positive will still be on the top. However, the current direction is going to change, and capacitor starts acting as a battery. So current start coming out of the positive side. So if you are trying to figure out what is X equation for the current, then you use negative C dV over dt if you know the voltage expression, because again, the current direction is opposite as compared to the equation that we write, IC is equal to C dV over dt, and that IC is entering into the side where you have the positive polarity. So in this case, we have negative L d over dt I naught E negative t over tau, and that is going to be I naught times L E negative t over tau, and then derivative of e to the power. I already took care of that negative sign because the derivative of e to the power negative x is going to be e to the power negative t over tau is going to be negative 1 over tau. So that negative and this negative is going to become positive, and then we have tau over here. So the voltage expression is going to be, let's say, V is I naught times L divided by 37.78. 37.78 e to the power negative t over tau voltage. That's going to be the voltage expression. So this is the current expression, and this is the voltage expression. And observe again, it's the same, the time constant concept is the same for the voltage as well. There's a time that it's going to take 36.6% of 37.78 volt, drop down to 36.6% of 37.78 volt. That time is going to be the time constant of the circuit. So irrespective you're calculating the current or you're calculating the voltage, the time constant definition in RC circuit and RL circuit is going to be the same. So definition is not like, oh, time constant is L over R. No, that's not the definition. That's the formula to calculate time constant. So remember, definition is the time that voltage or current is going to drop down to 36.6% of their peak value. All right, part number 3 is PR2 at 10 milliseconds. And actually, let me do part 3 here. All right, the first thing is, what will be the expression for PR2? So we can plug in the time and get it at 10 milliseconds. If you look at the circuit, actually look at the other circuit, source free. If you look at the circuit, PR2 is very simple, IL squared R2. IL squared T times R2. All right, so our ILT is 0.606 e to the power negative T over tau, square that R2. So we're gonna have 0.606 square R2 e to the power negative 2 T over tau. That's the power expression. So we can calculate PR2 at 10 millisecond, plug in the value 10 millisecond in the equation and get the result. Time is equal to 10 millisecond and PR2 is 0.606 times R2 times exponent of negative 2 times T divided by 17.403 watt. 17.403 watt. That is the power dissipated in resistor 2 at that instant of time. So not a very complicated problem, rather a straightforward problem. And we calculated 3 quantities in this problem. Let's keep doing problems. Let's go ahead and do another problem. Problem number 2. Okay. Let's see if I find a problem in the book. All right, let's do this problem. Okay, we have a voltage source. Let's call it VS1. It's assign a value 10 U negative T volt. And we have a current source. Let's call it IS2. And let's say this is 5 U of negative T milliampere. We have R1. Let's say this is 200 ohm. R2 is 330 ohm. L is 5 Henry. R3 is 410 ohm. R4 is 570 ohm. And R5 is 1 kilogram. Current IL. And let's say, of course, you can see both sources, their unit step function, they will be operating before time t is equal to 0, and they will be they will not be operating, they will be out of the circuit at time t is equal to 0. So determine determine ILT for t greater or equal to 0 or 2. Let's see. Power dissipated in R4 for t greater or equal to 0. So the expression for power dissipated in R4 for t greater or equal to 0. Let's find these two things. And then, of course, you can plug in any time value to get the power at that instant of time. So the first thing that we do, of course, is we evaluate the circuit for less or equal to 0. Specifically, we evaluate it at 0 negative to get the initial value of the inductor current. So the circuit, the sources are active before t is equal to 0, must be running for a very long time, and inductor will be acting as a short circuit. So you have to first calculate the initial value of the inductor current IL. We call it I naught usually. So let's see how you're going to calculate that from the circuit. What is the easiest way to calculate that current for the circuit? So let's redraw the circuit and show inductor as a short. You don't have to do that if you have the circuit though. Keep redrawing. I'm just going to draw it just for the sake of simplicity. 1, 2 resistors. Inductor is short. Another resistor. Another resistor. And another resistor. And the current source. VS1, IS2, R1, R2, R3, R4, and R5. R1, R2, R3, R4, and R5. Okay. Let me go ahead and plug in the numbers in my octave. So my VS1 is 10, my IS2 is 5 milliamp, my R1 is 200, my R2 is 330, my R3 is 410, my R4 is 570, and my R5 is 1 kilo ohm. Inductor is 500. These are my values. Now looking at the circuit, and we are trying to figure out this current, I naught, which is the inductor current. So looking at this circuit, and to find I naught, multiple things we can do that. Of course, we know that in this third loop, IS2 is the current that is flowing in the third loop. So if you want, you can apply KVL. And if we call this loop 1, loop 2, and loop 3. So loop 3 has already current IS2. And you can apply KVL in loop 1 and loop 2 to find the current I naught, which will be either sum of the currents in loop 1 or loop 2 or difference of the current based on the direction that you are taking. So that's one thing that we can do. Perhaps we can just do that. Not difficult. So let's assume this is current I1, and let's assume this is current I2. And of course, the current here is IS2, so we don't need to find that. So KVL in loop 1, we have VS1 as my source is equal to the voltage drop across R1 and R2, which will be I1, R1 plus R2. And Then the current passing through R2 is I1 plus I2. So I'm going to put I2 R2. That is going to be my equation number 1. And when we apply KVL in loop 2 and perform mesh analysis, then there's no voltage source, so 0 equals I2 times R2 plus R3 plus R4, and then I1 times R2. So I1 times R2 plus I2 times R2 plus R3 plus R4. And then R4 IS2 is going down, so minus IS2 times R4. We can bring IS2 R4 on this side of the equation. That's a constant value. And rest on the other side of the equation. I1 R2, this is R2, plus I2 R2 plus R3 plus R4. And that's our equation number 2. We can solve these two equations using matrix inversion method, then find I1 and I2. Let's go ahead and do that. So my constant vector A from the two equations for I1 and I2 is R2 is R1 plus R2, and then R2 for I2, and the next equation is R2 and R2 plus R3 plus R4, R2 plus R3 plus R4. That's my constant vector. And my constant, that's my coefficient matrix, sorry, not constant vector, coefficient matrix of I1 and I2. And my constant vector on the right-hand side is VS1 on the first row and IS2 times R4 on the second. This gives us my current vector as my coefficient matrix, inverse of that, and C. So these are my two current values. Let's go ahead and plug that. What is here? So this is my I1, and this is my I2. Interestingly, I2 direction is opposite. All right, so these are my two currents, and then my current I0 is I1 plus I2. I0 is I1 plus I2. Oh, I did not define that, so I'm just going to take the first value of I and the second value of I. 0.017714, so 17.7 milliampere. This is my initial value of current passing through the inductor. And now we're gonna do t greater or equal to 0. So when the sources are going to be 0, they will be deactivated. Current source is going to be open circuit. Go back to the original circuit. Current source is going to become open and voltage source is going to become short. So R5 and current source will be removed from the circuit, and the circuit will be reduced to R1 R2, R3, R4, and L. So let's go ahead and redraw the circuits. R1, R2, R3, and R4, and L. These are my 4 resistors that are left, R1, R2, R3, and R4, and inductor that is left. Okay, so this circuit is for t greater or equal to 0. And we are first writing the equation for ILT. I naught e to the power negative t over tau. And tau in this case is going to be 1 resistor, which will be the equivalent of all. And that is very easy to find out. R3, R4 in series, in parallel with R1, and then in series with R2. So R3 plus R4, they are in parallel with R1, and then this whole thing is in series with R2. There's my equivalent resistance, and L divided by this quantity, this whole quantity. That's my, so let's go ahead and calculate that. Now it's equal to L divided by R3, R4 parallel with R1. So RP, my function, parallel function. R3 plus R4 and R1 are in parallel. That's going to calculate the parallel. And I'm adding that into R2 plus R2. So one parenthesis here. And parenthesis here. So R2 plus parallel combination of R3 plus R4 and R1. L divided by that. 0.0100, so basically 10 milliampere. 10 milli, not ampere, sorry, 10 millisecond. 10 millisecond. Okay. I should just put short PNG. 10.08 millisecond. Okay. So that's my tau. I naught is 17.7 milliampere. So the equation for ILT is simply 17.7 e to the power negative t over tau milliampere. That's my first part. ILT for t greater or equal to 0. And then PR4, power and 4 equation for that. All right, so let's see how you're going to find PR4. Not difficult. We can find, because the ILT, the current in the branch, IL of course is acting as a source. So the current that IL is, the current that inductor is sending, that's going to be divided into R1 and R4 and R3, because those two branches are in parallel. So if we just find out what is the current going in the branch R3 and R4, then we can easily find the expression for the power. So let's apply current division. And find this current, IR4. So using current division, IR4, since total current is IL, is going to be equal to R equivalent over R4 plus R3 because they are in series with each other. And this R equivalent is IL R3 plus R4 parallel with R1 divided by R3 plus R4. That will be IR4. So IR4 is equal to, let's calculate this, R3 plus R4 parallel with R1 divided by R3 plus R4. And we can multiply that by 17.7 milli. Okay, so I'm calculating the coefficient of IR4. So let's call this IR4 is I naught, which is 17.7 milli right here. I naught times parallel combination of R3 plus R4, comma, R1. I'm assume that is R3 plus R4 parallel with R1, okay, and divided by R3 plus R4. 3 milliampere, 3.0024. I'm just going to take it 3. So that's going to be 3 e to the power negative t over tau milliampere. And since we know the current, therefore, the power equation in R4 is IR4 squared times R4, 9 times R4, 3 squared is 9, 9 times R4, e to the power negative 2t over tau, and then milli is going to, again, you take the square of milli, is going to become micro watt. Milli is 10 to the power negative 3. You take the square of that, 10 to the power negative 3 times 10 to the power negative 3. It's going to be 10 to the power negative 6. So that's going to give you micro. Let's calculate the coefficient. So P, let's say P naught is 9 times R4. Okay, so 5.13 exponent 3, and exponent negative 6. You're gonna be left with exponent negative 3. So you're gonna get, what is that, 5, right? You're gonna get 5.13 e to the power negative 2t over tau milliwatt. And that is the expression for the power in R4. Of course, you can put any value of time and you can get the power at that instance of time. Okay. All right. Let's see. So again, problems are going to be like these, not difficult problems. Can do one more problem. Okay. So pick a problem from the book and work on that. Let's do this problem. Problem number 3. Circuit is given. Very simple problem actually. You have a current source, IS, 12 milliampere, R1, 100 ohms. Switch is closing at T is equal to 0. R2 is 50 ohms. R3 is 200 ohms. R4 is 510 ohms. And L is 20 millihenry. 20 millihenry. Okay. And the question is, for the circuit, find ILT for t greater or equal to 0. So simple problem. It's one of the problems from the book that I picked up. All right, so again, observe that switch is opened for a very long time, of course. And then at t is equal to 0, switch is going to be closed. So when the switch is open, of course, no current is going through the switch. It's an open circuit. And inductor will also be acting as a short circuit after it is fully charged. So your circuit is going to be comprised of IS, R1, R2, R3, and R4, and replace the inductor with a short circuit. Now, when the switch gets opened, when the switch gets closed at t is equal to 0, then all the current, the supply current, is just going to go through that closed switch. No current is going to go through R1 because, of course, R1 will be in parallel with the closed switch. So all the supply current is just going to start flowing through the closed switch. That means your R2, R3, R4, and inductor, they will not be getting any current from the source, and they are going to become what? A source-free circuit. Okay, so let's go ahead and solve for I naught, IL T0 negative first. So at T is equal to 0 negative, I naught, which is IL 0 negative. Okay, how are we going to find that out? So our circuit is going to be, we can redraw the circuit real quick. IS and R1, R2, R3, R4, and I should not draw inductor. It's a short circuit. I'll just replace it with a short circuit right here. And short circuit. So we are trying to figure out this current I naught. Okay, so let's see. I naught, of course, is passing through R4. And let's see if I do combination of resistors. R4, R3 are in parallel with each other in series with R2. then I can find out how much current is going through R2 using current division, or the equivalent resistance, sorry, not R2. I can find out how much current is going through the equivalent resistance. And once I know what current is passing through the equivalent resistance, then I can easily figure out. Actually, I don't really have to do that. R4 and R3 are in parallel with each other. And the current is going to be divided into R1 and then the series combination of R2 and the parallel combination of R4 and R3. So once I know how much current is going through R2, then I can apply current division one more time to find the current I0. So I have to apply basic current division 2 times. One time to find what is the current passing through R2, let's call this IR2. And then once I know IR2, then I can apply current division between R3 and R4 and find what is the current passing through R4. So that's the plan. So let's apply current division to find IR2. Okay, so IR2 will be equal to the total current, which will be divided into R1, and then R2 and the in series with the parallel combination of R4 and R3. So the equivalent resistance R equivalent divided by R2 plus R3 parallel with R4. That's going to be one series resistance through which R2 is going to be flowing. The equivalent resistance is R2 in series with R3 parallel to R4 and the parallel combination with R1. That is your equivalent resistance. So IS let's write this down as R2 plus R3 parallel with R4 and this in parallel with R1. That is your equivalent resistance between R1 and R2 and the parallel combination of R4 and R3, which will be in series with R2. R2 plus R3 parallel with R2. Okay, let's go ahead and use our MATLAB. And we're gonna first put down all the values of the variable and then solve it. So once again, if it's all analysis, remember, if you do the analysis properly, solution is not an issue. You know, we are using a small function that we wrote to do the parallel combination and stuff. So we are not wasting time on that. We know how to do parallel combination, series combination. So there is no point of wasting time on keep doing those things over and over again, each and every line. That's a waste of time to me. So analysis is important. Once you have the correct analysis, then one line and you get the result. So IS is 12 exponent negative 3. R1 is 100 ohms. R2 is 50 ohms. And R3 is 200 ohms. R4 is 510 ohms. And L is 20 millihenry. Okay, let's go down. So I'm going to do first, let me just do the parallel combination of R2, R3, and R4 because I'm using it 2 times in the equation. So instead of writing 2 times, I'll do that. So I'll call this, let me just call it R equivalent is equal to the parallel combination of R2 plus R3. No, R2, R3 and R4, sorry, R3 and R4, parallel combination of that. And that is plus R2, right? So R2 in series with the parallel combination of R3 and R4. Let me just go ahead and confirm that. So R3 and R4 will be parallel if L is short circuit, and that will be series with R2. And that whole combination is in parallel with R1. Okay, so let's go ahead and do that. There's 193.662 ohms. And now my IR2 is IS times, now that are parallel between my R equivalent and R1, and that is divided by R equivalent, 4.08 milliampere. So let me just cut and paste this work as well. This is my IR2. Equals 4.08 milliampere. Okay, so now since we know IR2, that IR2 is going to be divided between R3 and R4, and we're going to go ahead and get the current that is passing through R4. Therefore, I naught, which is the current passing through IR4, is equal to, using again current division, IR2 is the total current, and the parallel combination between R3 and R4 are equivalent, divided by R4. Let's go ahead and calculate that. I naught is equal to IR2 times parallel combination between R3 and R4 divided by R4, 1.15 milliampere. 1.15 milliampere. So that is my initial value of inductor current, I naught. Now, for time t greater or equal to 0, t greater or equal to 0, switch is going to be closed, and IS, all the current is passing through the switch, and this inductor is going to become a source and it's going to start supplying current to R3, R4, and R2. Observe that through the switch, there will be two currents that will be flowing through the switch, the current that is passing through R2, and of course the current IS. But we are not concerned with that current. We are only trying to figure out what is the current IL. So let's go ahead and redraw the circuit. Let's see, what is that? Circuit. Okay, so R2, R3, R4, and R3, R4, and L. Alrighty. Very easy. We have IL, ILT will be equal to I naught e to the power negative t over tau. And in this case, tau will simply be R2 parallel to R3 in series with R4. Tau is, oh, no, tau is not that, that's R equivalent. Tau is L over that quantity. I keep forgetting about that. Tau is L divided by this quantity. So tau is L divided by parallel combination of R2 and R3, R2 and R3 in series with R4 plus R4 and parentheses 36.36 microsecond. 36.36 microsecond. So 1.15 e to the power negative t over tau milliampere. And of course, tau is 36.36 microamperes.